All righty. So before we get started with actual regression models, I wanted to talk a little bit more about bivariate probability distributions. So I know that so some of you were confused by these diagrams, and I just wanted to expose you to it again in order to make them a little bit less awkward to look at, so that you're getting more familiar to them. It's actually not that hard. I think it's more like a problem that we cannot really represent multidimensional things in 2D, right, in a 2D diagram. And that's what makes it a little bit harder, I think, to grasp. Okay, so when we are talking about a relationship between variables, so especially about correlation, right, or so simple regression analysis where we're focusing on two variables, so the relationship between two variables, we're always looking at bivariate probability distributions, so joint probability distributions for two variables, right? So often we denote them as X and Y, but this is of course arbitrary, so they can have any name or label. Okay, so we are talking about joint probabilities for pairs of random variables. And so that means that a bivariate normal distribution is nothing but a generalization of our normal 2D bell curve for a single variable to a bell-shaped surface. So it basically it actually looks more like a bell. So if they than our 2D representation. So or like I don't know, like a volcano without the hole in the middle. So if you have two unrelated variables. So if the two variables are correlated, so then it looks more like a fin, or I don't know how to describe that, right? So like, I mean, shark's fin has a slightly different shape, but it's like this round fin. So, so it basically describes the possible values of the two variables, right? So we are always focusing on pairs of X and Y. And I just want to explain it again, what a good way to look at these joint probability diagrams is, right? So here in this case, you can think about it as like, so the different slices. So you have for each value of your variable y, right? So you can see this here as, so you basically can imagine to cut that into slices, right? So this diagram, so that would be the first slice, second slice, the third slice, etc., etc. So you have for each value of your variable y, so you have a corresponding conditional probability distribution for your axis here, right? So of course, if we start here, so the probability, so the density is almost zero for all x, just because, so right, so the probability of having such an extreme y is also low. So that always means, right, so that's the conditional probability distribution for x. That means how probable is it to have axis of like these different values, let's say that is 1, 2, 3, 4, 5, etc., for a y that equals, say, this is 1, right? So discrete is always easier to think about. Let's assume, so this is the probability distribution for axis if y is 1. Yeah, so if I have, so you could think about it again as the relationship between, yeah, so because I called that 1, it's not a good example, but if you think about it again as height and weight, right? And so if x would be height and then y would be weight, so then the so if that is, I don't know, right, cannot be if that is 1 inch, right? So so then the probability distribution of what did I say? Height, weight. No, that must be, so then this is here. So this first row, of course, y is a weight. So let's say that is 1 pound, right? So let's say this is the weight in pounds and this is the height in inches. Doesn't make too much sense, right? But doesn't have to be humans. So then, so this would be right for your weight of 1 pound. So that would be your probability distribution of all the possible heights in inches, right? So of all possible value of height in inches. So, and as you can imagine, right, for this particular case, so these probabilities are low. And then if you basically get to values that are more likely, so more probable for y, for your weight variable, right? So let's say, so I don't know, maybe we're talking about dogs, right? So 20 pounds is like your, so it's like the most common, the mean for your weight. So then you see, so what is the probability distribution of height for this particular weight, right? So this is basically basically for all dogs that weigh 20 pounds, what is the distribution of their, as a probability distribution of their heights, right? So, and we can see that here, right? So then it's so basically the most likely, or the most, actually for the mean, it must be this one here, so the highest one, right? So the most likely, so the most frequent weight height for like the 20 pounds is of in this case also the mean height, right? So alrighty, I hope that helps a little bit, right? So you can think about it, right? So for basically this is a conditional distribution. I'm just basically explained it in this direction. You can also, so the same direction, right? So you have here, you have the conditional distributions of y, so of your second variable for each given value of x, right? I just did it in this direction because it's a little bit easier to see the lines here, right? So you have your, so for each y value, right, you have your corresponding bell-shaped probability distribution. Okay, is there a question or? Just okay. So in this representation is what is probably more familiar for you, right? So when you think about this, so the scatter plots of how we usually plot the correlations, and then we have these, and we have this ellipsoid here if there's a relationship. And so here it's just color coded, basically instead of a 3D representation. So we have just a color coded or a shade coded probability representation, right? So in the sense that the darkest area here is where you, right, so it's the peak of this little mountain here. So the darkest areas are these values here. So these combined values, these X, Y pairs have the highest probabilities, and this medium gray, so that's a little bit lower, right? So that would be here, it's like this basically lower portion of our mountain, right? So the density is lower here, and then so this light gray would be sort of the plateau, and then everything else here is more or less a plane, right? So where we have the flat area here, so the probability is close to zero. Yeah, so I hope that makes it a little bit more, so a little bit clearer how to read that and what is meant by that. So these bivariate normality distribution graphic representations. Okay, so in just, this is just a reminder. So we were talking about the probability mass function, right? So it's just the probability distribution of discrete variables. So that just means, so it's always easier to think about discrete variables. So everything applies to continuous variables as well. So the mathematical formula, the representation, of course, changes. But I'm sticking with the discrete cases here. So the principle is the same, and it's always easier. The formulas are easier, right? And it's easier to think about it. So, but basically everything I'm saying is also applicable to the continuous space, of course. So, and so it's, as you may remember, so for the probability distribution of a discrete variable, so our y value, so what this function describes is just so the probability of each individual possible outcome for a variable x, right? So that was what our probability distribution, so it's a probability mass function. So now that we have two random variables, right? We have x and y, so we have pairs of observations, and we would like to study them jointly. So we have a joint probability mass function. So we have a joint probability mass function, and we can generalize that to a multivariate case, right? So that's from bivariate to like multivariate, right? But then it's really hard to visualize that or to think about it. So the multidimensional space. So let's stick to the bivariate case here, which we are currently focusing on in our analysis, right? And we're talking about correlation in the simple regression analysis. And then later we might extend that model. So, and what you see here is the joint probability mass function of two discrete random variables, right? And that is nothing but the probability that X takes on a particular value and Y takes on a particular value. Yeah, that could be, if we go back to our example with the dogs and the height and weight, that could be, for example, so one potential value, probability value, might be the probability that a dog weighs, no, a dog is 10 inches, so has a shoulder height of 10 inches and a weight of 10 pounds, for example, right? So, and here, this is so the joint probability mass function in a very, very simple case. So think about it as so the variables X and Y as two discrete variables. And so they are the points that you can get for a single talk, right, in our seminar, right? So as those of you who attend the seminar, I think most of you know that every week. So when you're attending a talk, you can get 0, 1, or 2 points, right? So that is these are the possible values. And so let's assume, so this is so the first talk, right? And these are the potential outcomes, so 0, 1, and 2. And so Y is a talk in the next week, right? Also with the outcomes 0, 1, and 2. And then so on this third axis here, so the Z dimension, so this is just a probability, right? So, and I could, for example, say, well, what is the joint so probability mass function for these two, for the points in these two, for these two talks, right? And then I have so the following options, right? I could have, so my mouse keeps disappearing. So I could say, what is the probability of having 0 points, right? So that so basically how many students actually have, so this is of course not a good example because not that many students have 0 points. But so this would be basically, so this is the height here, right, would be the probability that somebody, so that we have 0, 0, right? So for 0 for talk 1 and 0 for talk 2. And here, so that would be the probability of getting 1 point for talk 1 and 0 points for talk 2, right? This would be the probability. So this the height here represents the probability for getting 1 point and 1 point, right? So this is a probability for getting 1 point this here. No, so this is a probability for getting 1 point talk 1 and 2 points talk 2, etc., right? So that it's basically, that's how for a discrete variable with very limited number of values, the joint probability mass function would look like, right? It's a probability of that X takes on a particular value and Y takes on a particular value, right? And then it's over all possible combinations of X and Y. Does it make sense? I can't see you, so you have to tell me.
Yeah.
Okay.
Yeah, that makes sense.
All right. So, okay, we can say the same thing. Basically, we can apply the same logic to the cumulative density function. So, or the cumulative probability distribution. So remember that for the discrete case, right? So that was so the CDF was, so the cumulative distribution function was defined as a probability that a value is so the same size or smaller than a particular, right? So that I get or obtain, so that I observe a value that is so equal or smaller than a particular value, right? So it could be for our dog example, if we would focus on height only. So then we could say, what is the probability that a dog has a shoulder height of at least 10 inches? So does it mean, what's the probability of a dog being like, yeah, 10 inches tall or shorter? And now that we have two random variables, yeah, we would like to study them jointly. So we can define a joint cumulative distribution function. So in the very same way as we define this joint probability mass function, right? So we now say, what is a probability for x being smaller than a certain value, or smaller or equal to a certain value, and y being smaller or equal to a certain value, right? And so that we can always interpret this comma as an and, so which basically turns our function into the probability that x is smaller or equal, so it's less or equal than a certain value, let's say, right, in our dog example, 10 inches, and so that the weight is less or equal to a certain value, let's say 8 pounds, right? And so these are just arbitrary numbers. All right, and that is just a little bit repetition from last week, right? So of course, for a bivariate distribution, each variable has a mean and a standard deviation. And we denote them as mu x and sigma x for so one of the two variables, and so mu y and sigma y for a second variable. And so then the way that these two variables vary together is described by their covariance, so which is defined as the average cross product, so the expected value of the deviations of an x value from the mean of x multiplied by the deviation of a y value from the mean of the mean of y. And so for the correlation, right, we just have to divide by the standard deviations. And so that shows us that the correlation coefficient is the expected value of the product of our z-scores, right? So if we know if we do a z transformation, then the standard deviation is one of the variables. So in this case, if we have standardized variables, then our correlation formula can be simplified to this format here, right? So it's the expected value of the product of the two values, right? So that's basically the average product of our two values. That is for standardized variables. All right. So after this theoretical introduction, a little bit dry, so let's talk about linear regression. So it's just important that these concepts that I mentioned earlier, that you're familiar with them, because in order to understand regression and linear models, so we will get back to them, and basically if these concepts are completely unclear, then you probably have difficulties fully understanding the regression analysis or linear models in general. Okay. So what is linear regression? So linear regression is a hypothetical model of the relationship between two variables. And when I say two variables, then I mean simple regression. Right? So we will talk about that after spring break. So we have also regression models where we have more than two variables. So that's called multiple regression. But today we are focusing on simple linear regression. So in the model that we're using in simple linear regression is a linear model. So we describe the relationship between the two variables that we are focusing on as the equation of a straight line. So very much the same that you know from correlation already. And so correlation and regression are closely related. And so we will talk about the exact relationship in a moment. So that means that simple linear regression is a model to predict the value of one variable. And this variable that we are trying to predict is referred to either as response variable, it can be called the outcome variable, it can be called the criterion. And we try to predict this variable from another variable. And this variable is either called our predictor, our explanatory variable, right? So there are different terms for that. Sometimes people speak about independent variable. So they refer to the predictor as the independent variable and the predictor as a dependent variable. So when you read different textbooks, so you will come across different terms, right? So, but the important thing is that regression is about prediction. really try to predict the value. Not only estimating the nature or the strength or the direction of a relationship between the two variables, as we do with correlation. We are really trying to predict the value of one variable, of our outcome variable, from another variable, which is our predictor. So typically when you read introductory textbooks, then other textbooks, so the response variable is denoted by y. So y denotes the response variable, letter y, and so the letter x denotes explanatory variable. But then again, so that is completely arbitrary, right? So don't get too attached to these letters. And that might change, right? So if you move to different models or like different textbooks, so there's nothing special about X or Y, so it's just a convention, and so right, they could be replaced by any other labels. Okay. So how is regression related to correlation? Yeah, so, and sorry, let me just, let's see, animation was not correct, so just pull that up. So correlation and regression are related in the sense, so they're basically closely related, or they are referring to similar scope of analysis, to the sense that they both deal with a relationship among variables. Right, so if it's simple regression and correlation, so then we are talking about relationships between two variables. They both deal with a relationship among variables. However, so correlation is more limited than regression. So correlation is a model that only cares about the strength and the direction of a linear association between two variables. However, simple linear regression is a model that also, in addition to that, right, aims to predict, so it attempts to predict the value of one variable from the other. Right? So if you know that two variables like correlate, and you know that the correlation coefficient is 0.5, right? Then, and let's say for your, so it's a dog example, right? So you have the height, and you try to predict the weight, and you know that height and weight so correlate, and that's a correlation. The strength of correlation, the direction can be described as a positive relationship, right? And so the strength corresponds to a correlation of 0.5. So it doesn't really help you to predict the so if you had like an individual dog, right, and you know that the dog weighs is like 12 inches tall. So then simply knowing the correlation won't necessarily, so without any further information, won't tell you, so you won't be able to tell what is the weight of this dog. However, so regression makes that possible, right? So of course, I mean, that is a little bit of an oversimplification. So if you have like a certain additional information, you can tell from the correlation as well. But so in general, so what the point that I'm trying to make is that correlation really only cares about the strength and the direction of the relationship, whereas simple linear regression is really about predicting the value of the other variable, the second variable. Yeah, and so we're so the model that we're using is a linear equation, and so the regression. So in regression, we estimate the parameters in this equation. Right, so these are our parameters, and that's also when we are making inferences for regression models. So then we're making inferences on the true parameters for this model in our population. And multiple regression is simply an extension of this model. So we use to predict an outcome from several predictors, so more than one. And it is a hypothetical model of the relationship between several variables, right? So not only two. And it's very important to keep in mind that neither regression nor correlation analysis can be interpreted as establishing a causal relationship between our predictors and our outcome variables, right? So that is something that regression analysis cannot answer. So either you make sure that in your experimental design that you can make such inferences, right, about the causal relationship, or you could use certain other statistical methods of being, for example, path analysis, also dynamic causal modeling. So where you are trying to make statements about the causal relationship between so your predictors and the outcome variables, but regression or correlation alone so basically cannot be interpreted in such a way. Okay, so let's talk about an example, right? So let's assume that a record company is interested in predicting record sales from the number of times an album is played on the radio. So let's assume so that our data would be 200 different album releases. So that we have 200 from 200 different artists. And so our outcome variable would be so the sales numbers, or this is the so it could be, for example, operationalized as a number of downloads in the week after the release of the album. And our predictor variable would be the number of times per week, right? So that songs from a given album are played on the radio. Yes, okay, that's meaningful. Not as an example, but so that could be so one thing that we can answer with a regression analysis, right? So if you want to know, can we predict the number of downloads, so how many albums are sold from how much we advertising this album. And let's say the advertising in this case is the number so that the album is played on the radio. Yeah. Okay. So of course, so the examples for regression analysis are endless, right? So we can predict insulin sensitivity scores from oral glucose tolerance test scores. We can predict receptor number from age. We can predict blood pressure from drug dosage, etc., etc., etc. Right? So I encourage you all to come up with your own examples. And so, right, simple regression might not always be the best model, because we know that normally in real life, so most phenomena are complex. So usually we cannot predict a phenomenon very well by focusing only on one variable. So typically we have to focus on multiple variables, but still, so it is a reasonable approach in many cases. Okay. So we have talked about that. So simple regression, linear regression assumes a linear relationship between predictor and outcome variable. Now we want to talk a little bit, so in more detail, what this linear actually means. So we have talked about the straight line a lot, but so let's put a little bit more meat into this concept here. So so when we say our regression model is a straight line, so then we conceptualize that as follows, right? So we are calculating our outcome, so the value of our y variable, or outcome variable, as so some intercept term plus the weighted predictor variable, or variables, right? So it can be more, but so right now for simple linear regression, we're focusing only on one, and some error, right? Some error term, so something that remains unexplained. And in mathematical terms, that looks like follows, right? So we have y equals b, so 0, and you often, I mean, that's something that you often know as an alpha or a or whatever. But so I mean, again, I could use whatever we want to, right? It's just a placeholder or some abstract label, right? So this is our intercept. This is called the intercept. This is called our slope, right? And then again, we have the error term, we have our predictor variable, and here our outcome, right? And so, and these two terms here, So the intercept and the slope, these are our regression coefficients. These are our parameters. That's what we are trying to estimate, right? So when we are trying to predict our outcome from our predictor, from our explanatory variable, so we have to estimate some weight that we multiply our explanatory variable with, and then we add some constant in order to predict our outcome, right? And then we are, so typically, so because in social science, or even in, not only social sciences, but also in neurosciences, or generally in sciences, so we don't have a perfect prediction. So that means there's always some error term, so some deviation between our prediction and the actual value, right? So we cannot perfectly, if we go back to our weight example, right? So if we wanted to predict the weight from so the height, then typically, so this prediction won't be perfect. So that means that for an individual dog, so the weight might deviate more or less from the prediction. Okay, right. And again, so these are the parameters that we want to estimate. Okay, so now let's talk a little bit about what these regression coefficients actually mean. So let's start with our intercept. And again, so you may be more familiar with an A or an alpha. I call it B0. I just do that because when we move on to multiple regression, it's more common to basically label all regression coefficient as B than just these indices, right? So just numerical indices to enumerate them. That's why I make this transition here. So there are other slides where I have the alpha. So I'm changing a little back and forth also to encourage you to think about it in a bit more flexible terms, right? And remind you that these are just placeholders. So, okay, right? So what is the intercept? So here, right, so again, so here we, right, so we have our regression line here. So that is our straight line, and it can be described by this equation, right? So intercept plus, so the slope times x, so times the value of our predictor. And so we will talk about what this little head here means in a second. Okay, and then here's these black circles, right? So these are our actual data points. Okay, so and then we see that so our regression line here, at some point, so it hits the y-axis, right? And then, so our intercept can simply in mathematical terms just be described as a point basically where the regression line crosses the y-axis, right? And it is the, simply it is the, so it is the value, so the expected value of y, so the expected value of our outcome variable when x equals 0. Yeah, and it's, so we will have several examples later. Sometimes we can interpret our intercept in a meaningful way. Oftentimes we cannot, right? So, but it is where the regression line crosses the y-axis. It is the expected value of our outcome if the predictor equals 0. Okay, then our second parameter, well, that is a slope. What is the slope? So the slope basically indicates, this is shown here, right? So the slope is basically this yellow vertical line here. And the slope tells us, so if my predictor changes by 1 unit, yeah, so for our dog example, it could be, so the units could be inches, right? So let's assume that is 1 inch. Don't worry about the scale right now, whether that makes sense or not. So if our predictor changes by 1 inches, right? If I go from 2 inches to 3 inches, for example, then how much does the weight, the predicted weight change? Yeah, so if I go from 2 inches to 3 inches, so what for dogs not very meaningful. Okay, maybe rather guinea pigs now. So what is the corresponding change in our predicted weight? Yeah. And that distance here So the change in y, the change in our outcome variable per one unit change in our predictor variable, that is the slope of our regression line. And that is what we estimate here. So that is our second parameter, right? So our regression rate here. Okay, so, and so then, so we have here, right? So we have a specific value of our independent, right, variable or explanatory variable, our predictor variable x. Again, let's think about it in terms of height. Now let's say these are, I don't know what, yeah, 5 inches. And so then we basically, so we move all the way up to our regression line, right? And so, and then when we hit the regression line, so then this will be the expected, so the predicted value, that is the value in weight. Yeah, so that is the value in weight that our model predicts for an animal that is 5 inches tall. Right? And so we might have one animal where actually, so this is exactly right? So I mean, that would be a little bit off here. So that actually exactly where the weight is exactly the same weight as predicted by the model. However, that is rather rare. So in most cases, like here, right, so that's a second animal that has the same, basically has the same height, so it's also 5 inches tall. So, but this animal so has actually a higher weight than is predicted by the model, right? So, and this is the error term, the deviation from what is predicted, right, by our model equation, and what the outcome variable actually is. And so it's important that, of course, so these individual observations can deviate either in either direction, right? So sometimes we are underestimating the weight as for this animal, sometimes we are overestimating the weight as for this animal, right? So, and they are basically just, they're spread around this regression line here. So one more thing so that I want to mention here. So we differentiate between our so the regression. It's actually a bit confusing because regression coefficients are typically denoted by the letter B. If they are denoted by the beta, so by beta, so it's a Greek letter, then they sometimes, but that is not always the case. So sometimes that means that they are standardized beta, so standardized regression coefficients. And so that simply means that so they are expressing a change in standard deviations and standard deviation units. So rather than, for example, standardized beta doesn't tell you so how much the the outcome variable changes per one unit change in the predictor, but it tells you how much the outcome variable changes per one standard deviation, right? So if you have a change of one, so basically that is the change in basically in standard deviations of y per standard deviation of x. Now that makes it more comparable, right? So if you want to, it's the same as for correlation, right? If you want to compare our regression coefficients across different variables that have different variations, then so it might make sense to standardize the regression coefficients and always express them in terms of standard deviations of x and y, so of predictor and outcome variable. So per standard deviation change in the predictor variable, how many standard deviations or fractions, right, of the standard deviation changes the outcome variable. Now that's a standardized regression rate. And the confusing part is that also sometimes the basically the population parameters are so of the regression rates are labeled as beta, so you never know 100% what it means. So it could be one or the other. So ideally, so it will always say. But if you read standardized, that's what it means, right? So and the standardized betas are just so the beta weights for if both the predictor and the outcome variable are z transformed. So if they are known. standard normal scale. All right, so I want to say a few more words about the residuals because they're very important, and I want to make sure that everybody understands what is meant by a residual. So here is an example from the textbook where so the explanatory variable or the predictor is a poverty rate, and the outcome variable is a murder rate. And here, so the different observations correspond to different cities in the United States. So here our subjects, right, our observation units are cities, so not animals or humans. And so right, so what is shown here is, so this is for LA, so for Los Angeles. So we have the poverty rate, which is pretty high here, over 25. And then we also have a pretty high murder rate. So, but here, so this is our regression model, right? So that is basically the model that predicts what the murder rate is based on the poverty rate, right? And so if we go down for LA, right? So then we have poverty rate of, let's say, 26, right? So 26, and then our model would predict that the murder rate for such a poverty rate is like just below 15. So it's 14, right? But actually the murder rate in LA is higher, right? So we are underestimating the murder rate. And so with this model, we focus only on poverty as a predictor. So in this difference here is a residual for Los Angeles. And then the other that could be here, I don't know, New York City and Boston and New Orleans. And I mean, I don't know what cities are in this sample, right? So and for some cities, so the murder rate is underestimated, is overestimated, like for this city, right? So for all these that are under the line, so under the regression line. So here the model actually overestimates the murder rate. And for all units that are above the regression line, the model actually underestimates the true murder rate. Okay. So the residuals are always a vertical distance between the prediction line, between the regression line, and the actual outcome value, right? So it's always so residuals are always referred to the outcome variable. This is our y variable, because that's what we're trying to explain. That's what we're trying to predict. And so we're caring about how much do these actual observed values deviate from our predictions. And it's also, so, right, and I didn't talk about the y hat. I promised you to do that. So, so actually the value that, so the y values, our outcome values that is predicted by our regression line. So those values are referred to as y hat, right? So y hat, and these are just predicted values. So that's what we predict for, right? For a city that has poverty rate 25, we predict this murder rate here, right? And this would be our y hat. Okay. So the difference between the actual y value and the y hat, so between the predicted value, again, always for, right, it's always conditional, right? So given a certain value of the predictor, that is called the residual. And obviously, so the smaller the absolute value of the residual, the better the prediction, yeah, because the predicted value is closer to the observed value. So let's go back to this fantastic example from the beginning. Let's talk about how to interpret the regression coefficients for this model. So let's assume that so somebody would have actually fitted the model, fitted the regression line, and would have determined that so our slope parameter is 3.87. And our intercept is 88.97. Right. So what does it tell us, right? And so here, so we have our predictor was a number of times a song is played on the radio, right? A song from this album. And here we have the album sales, so it could be like downloads or whatever. And that is in thousands, right? So so one unit here would be 1,000 albums sold. And here, so the number of times played on the radio, that is just, right? So 1 time, 2 times, 3 times. So the unit is 1 here. All right. So if that's basically right, and that would be our regression model here. So y, so the album sales equals, right? So 88.97. So that's our intercept, right? So that's where our regression line or predictor line crosses the y-axis, plus 3.87 times our the times that our predictor variables, so the times that the song has been played on the radio. Okay, so that means each time, yeah, a song from the album is played on the radio, the album sales increase by 3.87 units. So that means each time you play the song on the radio, so per unit change of the predictor variable, we are selling, so the prediction is that we are selling on average 3,870 albums more. Yeah, so 1 unit change in the predictor corresponds to 3.87 unit changes in our outcome variable. So because a unit for the album sales were 1,000, right? So this corresponds to, right? So if you basically per radio play, so 3,870 more albums are sold. So and what does our intercept mean here? So that is basically so in this case, where we have actual, so we really have data for so 0 times played on the radio. That means in this case, we can actually interpret our intercept. So and that it means that so if we basically, so this is our base, is a baseline measure, right? So if we would never, so if a song is never played on the radio, if basically if it's not advertised, so how many albums are sold in this condition, right? So what is a baseline of album sales? And so in this case here, it's 88.97. So that means if an album song is never played on the radio, so the average number of sales is 88,970. Yeah? And then each time it's played, we increase that by, so we basically we sell 3,870 albums more on average. Okay, so and as I mentioned, so we so that would be one example where we actually can interpret the intercept in a meaningful way. Often we cannot. So we can interpret it if we have data, if we actually have data where we have observed a value of 0 for our predictor, right, as here. So we have certain albums that were never played. So in this case, we can interpret the intercept in a meaningful way, as in this baseline way. However, so if you think of another study, so let's say you're interested in so age and income. So, and then your participants are between 25 and 70 years old, and you're trying to predict income from age. So then it's very questionable whether it actually makes sense to interpret the intercept of like age 0. So that would be a newborn. Yeah. So is that really meaningful? Probably not. So and so that's why if you basically some people rather than using so the raw values for your predictor variable, so they actually subtract the mean from the predictor. And if you do that, you can always interpret your intercept in a meaningful way, because then it's simply the value of your outcome that is predicted for the mean of your predictor, right? So if you would do that for the age example, if you have basically what if the mean of your sample would be 50 years, and you would subtract for each participants so the mean age, then your intercept would be the expected income for a person that's 50 years old. Right, so that it would make more sense, and that's why in some studies they center as a predictor if they in order to have like a meaningful interpretation. It doesn't really matter. So mathematically it's equivalent. It's just if you want to, if for whatever reason you want to interpret your intercept. Okay. Yeah, so that is just to reiterate that, right? So each time per week a song is played on the radio. So if I have 1 unit change in my predictor, the album sales increase by 3.87 units. Yeah, because 1 unit corresponds to 1,000 albums sold. It means that so 3,870 albums, so more are sold. Okay. Okay, so now let's talk about it. Let's talk about how we estimate the regression coefficients. So how do we do that, right? So we want to come up with, of course, a prediction for our outcome variables that is as good as can be, right? So we want to estimate so the intercept and the slope in a way that so we have the best fit here. So then the question is, what is the best fit? So how could we quantify that? And I mean, no. So normally I ask that, but because it's on the slides anyway, so it probably doesn't make too much sense. So obviously, I mean, we mentioned that already. So a good way is to focus on the residuals. So on the deviation of our data points, so the actual observed data points from the predicted values, right? So here in this graphic, all these, yeah, what does it take? What color is it? It's not, what is it called? Tail? No. Come help me. What's the name of this color here? It's a bluish.
It's like, I want to say baby blue, but Patrick just said aqua on the chat.
Okay.
I was going to say teal, but teal is more greenish, so we're just gonna go with aqua.
Aqua. Okay. So the aqua colored dots, these are actually observed values for the outcome variable, right? So that would be the weight in our example where we try to predict the weight from height, right? So these are actual observed outcome values. And the red dots here are the predicted values, right? So this is what the regression, the prediction line here or regression equation would predict, right? So for a given, of course, right? So always think about this. So each value here corresponds to an x value, of course, not on this imaginary line. Okay. So and then the the residuals, right, are simply the deviations from of the observed values from the predicted values. So and it would be a reasonable thing, right, if we would want these residuals to be minimal. So we want to estimate our regression coefficients, so the B0 and the B1 here, in a way that the average deviation of our observed values for the outcome variable across all observations is minimal. So and then so you could think, fine, so we will just, I mean, obviously, I mean, working with the raw values is not a good idea because sometimes it can be negative, sometimes it can be positive, right? So they will just cancel out each other on average, right? And then we have, so that is not good. So then one could say, fine, so we're just working with the absolute values, with the absolute deviations, right? So we don't care whether it's a negative direction or positive direction. So we are focusing on the absolute deviations, and our condition for estimating these parameters is that the absolute deviations are minimal. So the sum of the absolute deviations, right? So summed across all observations. And so there's nothing wrong with that approach. So it's perfectly fine. It just has very undesirable mathematical properties. It's actually really, really hard. So if we're working with absolute differences. And that is the main reason why we're focusing, or why so the estimation of the regression line is based on squared deviations, right? Because it's the same effect. So we, by squaring the deviations, so we get rid of this problem that they're sometimes positive and sometimes negative. So and so basically the condition for estimating these parameters is, okay, so we want to estimate them in a way that the average squared, so the sum of the squared deviations or sum across all observations is minimal. And another requirement that we have is that on average, the deviations are 0. Right? So on average, the residuals are 0. Yeah. So and the and then the squared deviations are minimal. So these are the two constraints that we have, and that's how we determine the regression line, the equation. Yeah. Okay. Yeah. So our residuals, that's the first condition. Residual should be 0 on average. Yeah? The sum of our residuals should be 0, and the sum of the squared residuals should be minimal. And then, so we can solve the equation. So what we do is the ordinary least squares method. If you use the OLS, so you might read that occasionally. There's nothing but that. It is exactly so this requirement. And what you do is you calculate the partial derivatives for the equation model. But so for the regression model. But so we don't want to focus on the math right here. So basically, but what I want you to understand is so these two requirements, right? So that is basically the condition for estimating the parameters. All right. And so if we do that, then so the our intercept is simply calculated as the difference between the mean of our outcome variable and then the weighted mean of our predictor, right? And it's weighted by the slope of our regression model. And our slope parameter is nothing but the covariance between x and y, so between predictor and outcome variable, divided by the standard, by the variance of x. Yeah, so it's covariance x and y divided by the variance of x. Yeah, so it's basically corresponds to this change, basically the change of y per unit change of x. So it corresponds to that. Alrighty, so and it's always important to know, right? It must be the case. So the regression line always passes through the point. So basically the x bar, y bar, so through the means, so point that is defined by the mean of predictor and outcome variable. So the center of the data. All right, so now it's getting a little bit more theoretical again. But again, that's important to understand the assumptions of regression later on. So especially homoscedasticity, so that we will talk about after spring break. And has to do with bivariate normality. So it's a side effect of bivariate normality. All right. So our regression model is a probabilistic model. So what does it mean? It's not a deterministic model. If it was a deterministic model, then our regression equation would always predict so the outcome variables, so the value of the outcome variable without any error, right? So then all our observations would be exactly on our straight line. So that would be a deterministic model. So that is typically not the case, right? Especially not in psychology or neuroscience. So in most, so all applications, so we are talking about a probabilistic model for the relationship between x and y. So that means that our regression model allows for variability in y, in our outcome variable at each value of x. Yeah, so that means our actual or observed outcome values will vary around these. So it will just spread around the predicted values. Right, so for the same, so that means that, so let's again go back to our dog example. For like 100 dogs that are all 10 inches tall, so the weights will be different, right? So we will have a distribution of weights that is not, right? So the standard deviations, the variance of this distribution will not be 0. So, right, and depending on how good our model is, so the spread of the distribution of the actual weights for all dogs that are 10 inches tall will be wider or narrower, right? Will be smaller if the prediction is better, and it will be wider if the prediction, if the model is worse. And so that also means that our probabilistic regression model, right? And here I'm using this different form, like in the textbook, where I denote the intercept as alpha and the slope as beta. So the probabilistic model is actually so that we're using that represents the mean of the y value. So that's what we're actually predicting, right? So we're predicting the mean of this distribution of y values around our predicted value. Yeah? So rather than so the outcome variable, so rather than y itself. So for our dog example, what we are predicting with our regression equation is the mean height of dogs that are 10 inches tall. Yeah, we are not actually predicting each individual, right? So there's always an error, right? So we are predicting the mean height of those dogs as a mean weight, sorry. So what that means is that for each given value of x, our regression equation, right? So our prediction represents the mean of the conditional distribution of y given x. Yeah, so it's a conditional distribution of weight given that the height is 10 inches or 5 inches or 15 inches. Yeah. So that means a regression function is a mathematical model that describes how the mean of the conditional distribution of the outcome variable changes according to the value of an explanatory variable x. Yeah? So how does the mean of weight change as a function of height? Yeah? That is what the regression predicts. So it's always important to keep in mind, right? So we are predicting, so basically, the actual outcome variables will always spread around the predicted values, right? Even if the predictor itself is the same, right? So for like again 100 dogs that are all 10 inches tall, their weights will be different. Yeah. All right. So let's take a look at that. So here's another example from the textbook, right? And that is the relationship between age, which in this case would be the predictor. And here actually it's, so we'll talk about that in a second. So that's another example, right, where we cannot interpret the intercept in a meaningful way. So age is the predictor, and then income is the outcome variable. So we want to predict income from age, right? So in this case. So, and then at any particular value of age, right? So 6 years, 8 years, 10 years, 12 years, 14 years, etc., etc. So our regression model, right? So it's expressed by this equation, estimates the mean, right? It estimates the mean of all subjects in the population that have this age, right? So that means here, right, for age 8, our regression model estimates the mean so the mean income of all individuals that are 8 years old in our population. Yeah, for the age 12, so our regression model predicts the mean income of all individuals in our population that are 12 years old. Yeah. So here it predicts the mean income of all individuals that are 16 years old, etc., etc. Right? So I'm saying here, so the regression model is so the expected value of y, right? So the expected income is minus 5,000 plus 3,000 x, right? So 3,000 times the age, and then minus 5,000. And so, and that shows, so it's a classic example where you cannot interpret the intercept. So that basically would mean that a newborn is born with debt. So it owns minus $5,000. So that does, it's idiotic, right? So, and clearly, so in this case, so newborns were not part of the sample. And so we cannot interpret that value in any meaningful way, which is just a mathematical entity here, but has no meaningful interpretation. And then our conditional, so basically the standard deviation of our conditional distribution. So that's basically the standard deviation of y given x at 13, right? And that is simply the standard deviation for these distributions here, right? So the standard deviation of this distribution is 13, standard deviation of this distribution at 13, standard deviation of this distribution is 13, right? And that is the standard deviation of y given x, yeah, because it is a standard deviation of y given age equals 8, yeah, y given age equals 12, etc., etc. So, and for our bivariate normal distribution, as you may remember from last week, so one condition was that for any given value of x, the standard deviation, right? So the variability of the y values is the same. So that means, right, if two variables are basically follow, or right, have a bivariate normal distribution. So then the standard deviation for each possible value of x, right? So standard deviations with the corresponding y values have to have the same standard deviation. And that is also called homoscedasticity. We'll talk about that after spring break. All right. So, right, and so this slide is just to show you that so right, so this again is our, right, just another example, right? So we're here, so high school GPA is a predictor and college GPA is the outcome. And then again, right, so for each value of the predictor for each high school GPA, so you have these, right, this represents students that all have the same high school GPA of, I don't know, 2.6, right, 2.6. And then you see the distribution of the college GPAs for those students, right? And the standard deviation of these distributions here, that is the standard deviation of y given x. And don't confuse that with the standard deviation of y as it basically in total, right? So that is a college GPA, that's a distribution for all students. So that means across all possible values of x. Yeah, so there's basically all students with all possible high school GPAs. So our standard deviation of the college GPAs is basically unconditional distribution, looks like that. And what you can see here is that the conditional distribution is typically smaller, right? And that is always the case if our regression model has any predictive power. So that means if our correlation between the predictor and the outcome variable of the relationship is not zero, then our conditional distribution here will be smaller than the unconditional distribution of our outcome variable. When it's zero, so when there's no relationship between predictor and outcome variables, and we're simply predicting for each value of the predictor, just the mean of our outcome variable, and then basically these conditional standard deviations will be identical to the unconditional standard deviation of our outcome variable. All right, so we have talked a little bit about how we might assess the goodness of our model in general, right? So we have talked about residuals, and we have said that if the residuals overall are smaller, so if we make a smaller error on average, so our model is better. So, and of course we want to know that, right? So when we're when our goal is to predict so our outcome variable, we want to know, is our model useful, right? So how practical is it, right? So can we actually make a better prediction than by just guessing, right? So right, so we have to find a way of testing how well the model actually fits the data. So how we're doing that. And so an appropriate measure to assess the goodness of fit, right? So how well our model actually describes the data is the coefficient of determination. It's called R squared. Yeah, so coefficient of determination. And R, so it means basically the square root of R squared, is simply the correlation between the actual values of the outcome variable. Yeah, so it's the actual weights of our animals and the values that were predicted by our linear model. So this is the y heads, right? So it's a correlation between our y, between the actual values, between the actual weights and our y hat. So these are the values that were predicted by our model, right? Let's go back here to here, right? So it is a correlation between the aqua points and the red points. Okay, and so R squared, so our coefficient of determination is simply the proportion of the variance in our outcome variable that can be explained by our predictor. Yeah, so R squared in the dog example, that would be the proportion of the variance in weight that can be explained by the height of a dog. Yeah? By knowing the height, how much of the variance, the variability in weight can I explain? And of course, the more I can explain, the better is my model. And also makes sense because of proportion, right? So that R squared is always between 0 and 1. If it's 0, then it indicates that the model explains none of the variability in the outcome variable around its mean. And if it's 1, then it means that the model explains all of the variability. So that would be a deterministic relationship. So, right, so that is just written down like in words. So variance of the outcome variable explained by the regression model over the total variance of the outcome variable. This is in mathematical terms, right? That is just the it's a variability of our y hats of our predicted values, right? It's a variability of our predicted values. That is just the average squared deviation of our predicted values, right? So from the regression line, from the mean of our outcome variable. And is divided so by the total variability. And that can also be expressed as a model sum of squares over the total sum of squares. So that term should sound familiar to you, right? Sum of squares. So you all should have heard that, right? From so typically sum of squares are introduced when you're talking about analysis of variance, about ANOVAs. Well, actually, you can use that concept when you're talking about any linear model. So let's just review what is meant by sum of squares and why are they important, right? So we have 3 main types of sum of squares. The first one is a total sum of squares. A total sum of squares is just a total variability. So a sum of squares, remember, right? So sum of squares is just the deviation from the squared deviations from the mean, right? So that is a total variability of a variable. So that's a variable of scores around the mean. Right? So how much do scores deviate from the mean? And of course, we are looking at squared deviations to avoid this problem of having negative and positive values canceling out each other. Then the second important type of sum of squares is a model sum of squares. It's also referred to as a model variability. And that is the variability that is explained by the model. Yeah, that's basically there's a regression line. It's the estimated outcome values in our regression model, right? So that is basically the variability of the points that lie on our regression line. So how much do they deviate from the mean? And then we have the error sum of squares. And that's just the residual, the error variability. That is the variability of the actual data around the regression line. Yeah? So that's basically the variability of the actual data around our estimated values. Yeah? So it's not basically the variability around the mean of our outcome variable, it's the variability around the regression line, so deviation from the regression line. All right. To make that a little bit more nicer, like a visualization, right? So here, so in the upper corner, you see a visual representation of our total sum of squares. So then again here, right, so this y, that is our outcome variable. So in this case, I'll stick with my great example of so animal weight or dog weight. Right? So this is a dog weight here. And this red line just represents a mean. That's a mean weight. So let's say a mean weight of dogs 10 pounds, right? And so these are the individual observations, right? These are like 8 dogs, right? So 8 dogs. So first dog, right, weighs 3 pounds, and we have on 5 pounds here, I think. No, 8 pounds, etc., right? So, and then the total sum of squares is nothing but the squared deviations of each individual dog, so the weight of each individual dog from the mean weight, right? So some are lighter, some are heavier, and then so we're calculating the square, right? So of each deviation, and then we are, so sorry, that should be a square here, I forgot that. So that should be squared, and then we are summing that across all our dogs, right, in our sample. All right, so, and then what is our residual sum of squares? So here we have the regression line, so that is our model that predicts, right, from our height, so the dog height, right, these are the corresponding values. So, and that is our weight. So what is the expected weight? So the predicted weight for a dog, right? So that is one. My inches are not very. My inch scale is not very good. Let's say 1 unit here, 10 inches, right? So dog 10 inches still too. Okay, 10 inches, 20 inches, 30 inches, etc. Right? So this is our model that basically predicts the mean weight of all dogs that are so 10 inches tall, 20 inches tall, etc., etc. So here we have only one measurement point, but in general, right? So we will have like more than one dog with that weight. All right. So, and the residual sum of squares is just the, right, that is the deviation of the individual weights for the individual dogs from these predicted values. Again, so we have to square. So sorry for this. So there has to be like a square right here that's missing. Right? We're just summing across all observations. And then what is a model sum of squares? So the model sum of squares. So that is basically the variability. So that can be explained by the model, right? So that means it is the squared deviations of our predicted values from the mean of the weight. So basically we don't focus on the dots, we now focus on the blue line, right? So it's basically, so we're calculating the so basically the deviation of the blue, right? The blue line from our for each height value, right? So the deviation of the blue line from the mean weight. Right? So we take that for each here, for each point, right? And then we sum that up across all observations, right? And calculate the square, and that is our model sum of squares, right? And that is the variability in our outcome variables. That is variability in dog weight that can be explained by our regression model, right? So these numbers here, right? So sorry, they're not this one, but that would be, right? So that would be the difference between the predicted weight and the mean weight. Not here, difference between predicted weight and mean weight. Difference between predicted weight and mean weight. And we are, again, so we calculating the square, we are summing up across all values, right? So. And of course, right, our total sum of squares, our total variability is simply the sum, right, of our model sum of squares. So basically the variabilities, the deviations, right? So the sum squared deviations of our predicted values from the mean of y, and then this unexplained variability, right? So it's just, right? So what is explained by the model, and then plus the unexplained rest. So what's left over. That is and that explains our total sum of squares, or total variability of the data. And our R squared is nothing, right? So our R squared is basically the ratio of our model sum of squares. So what is explained by the model over the total sum of squares. So the proportion of sum of squares is a proportion of variability that is accounted for by the model divided by the total sum of squares, the total variability. So what is a proportion that can be explained in the total variability? All right, so That's just another visual display, right? We have the total variance in our data. Then, so one fraction of this total variance can be explained by our model. That's a model sum of squares, right? So the total sum of squares. And then I have some error, some residual variability that I cannot explain. And so obviously, if there's no relationship between predictor and outcome, then the best predicted value for the outcome is its mean, yeah? Because on average, so the mean is per definition the value that on average, so our observed values, so the values of our variable deviate from the least, right? That is our mean. That's just how it's defined. So that means in this case, if we simply predict the mean, so if there was no relationship between dog height and dog weight, then our best estimate would be simply to predict the mean weight, right, of a dog, because that is a value that makes the smallest mistake on average, so the smallest error. Okay, so that means our model sum of squares would be 0. Our residual sum of squares would be equal to the total sum of squares, right? So our residual variability would be so the same. So it's all residual variability because so we model explains nothing, and our correlation between predictor and outcome would be 0. So from that follows that basically if we expect a regression model to do well, then we would expect the model sum of squares to be greater than 0 and the residual sum of squares to be smaller than the total sum of squares. All right, so regression model is always an approximation for the relationship between the variables in the population. So how do we make inference to the population then, right? So how do we determine whether the variability that is explained by our model, so whether that is actually something that we can generalize to the population? So there are two different ways. They're equivalent, right? So you can choose whatever fits your needs better. So it always depends whether you're more interested in prediction or whether you're more interested in the relationship between your predictor and your outcome. So the first way is that we test our R-squared for statistical significance. And that is based on what I just introduced, the sum of squares and the variability. So we're basically testing whether in our population, the true R-squared, so the true explained variability is 0. Yeah? So that is what we are testing. And our alternative hypothesis would be that our explained variability, so the variability in our outcome variables that can be explained by our regression model, is larger than 0. Now, of course, it cannot be smaller, right? That cannot be negative, this fraction that is explained. It can only be larger than 0, right? So it is better to use likelihood-based methods, by the way, than the classical significance test. But so we will talk about that later in the semester when we are talking about so the general linear model and other things that we right. And then we will also talk about likelihood ratio tests, which are in most cases a better approach. But right now, yeah, let's keep it simple. And you see the normal significance test logic. All right, so that is one way to test whether we can generalize as a population. Another way, that is, as I said, equivalent, is so to test the regression coefficients for statistical significance. And I mean, the intercept obviously doesn't actually matter. So the intercept is, nobody's interested in the intercept. So if I would standardize my variables, the intercept would be 0, it's always 0. So the intercept is just blah, right? We don't even need to focus on that. So when I say regression coefficients, I always mean the slope. So it's the only coefficient that we're interested in, right? So an intercept in itself basically just says, so the only thing that an intercept tells us is that there's a mean difference between, yeah, so that's it, the difference between, so there's a difference in mean between predictor and outcome variable. So that is not what we are asking in a regression, right? So, okay. So the second equivalent way of testing that we can generalize our regression model to the population is that we are testing whether our slope parameter is 0. Yeah? If it's 0, then obviously, so we have no relationship. We are always predicting that so the outcome variable, so for basically it's constant. So for each value of x, we predict just the mean. That would be our null model, right? Or for like that means there's no relationship. So we cannot, and that, so basically, so knowing the predictor, so knowing the dog's height doesn't help us at all to basically make a better prediction of their weights and the mean. So then knowing nothing about their height, right? So knowing the height actually adds nothing to improve our prediction. So it helps us, doesn't help us at all. So that would be the case where our slope is 0, so we just have a horizontal line through the mean of weight, right? So for all heights, we predict the same weight, and that is a mean weight. Okay. So, and our alternative hypothesis would be that the slope is larger or smaller than 0, right? So, so other than for the so coefficient of determination for R squared, so of course we can have a negative relationship. So it could be the case, I mean, in the dog example, of course not, but it could be the case that so the larger the predictor, the smaller the outcome, right? So then we have a negative beta, a negative regression coefficient slope. So we start with so testing whether we can generalize our determination coefficient to the population. So whether we can infer that, say, actually our the explained variance is larger than 0. Okay. In order to test this question, to test whether our regression coefficient or coefficient of determination is different from 0, we use a test that also should be familiar to you. That's the ANOVA F test. Okay, so why is that, right? So, I mean, we have talked about the sum of squares already, so maybe that gave you an idea, right? So why we can do that, but we will talk about it in more detail now. All right, so again, so we want to test whether our overall regression model, right? So basically our prediction or y hats, so whether this prediction is better than a null model. And once again, so as I said before, a null model is we simply predict, so or for all values of x, so for all values of height, we simply predict the mean weight. So that would be a null model. And so the ANOVA F test, or simply F test, is based on the ratio of variance of the outcome variables that is explained by the model. So that's basically the model variability, or the sort of a model sum of squares, versus the unexplained variance. That is our residual variability, right? So our residual sum of squares. So, and this is our basically test statistic for the F test. And so rather than using the total sum, so rather than using the sum of squares, we're using the mean sum of squares, so it's expressed by MS here. Because the disadvantage of the sum of squares is that they are dependent on the number of observations, right? So it's similar to the variance. So the more observation units we have, so the larger our sum of squares. That just must be, right? So, and that's not a good thing. So that's why we want to come up with an average, there was a mean, and that's a mean sum of squares. So in this formula here, or this test statistic, is basically just a ratio of the variability that can be explained by our model, and the variabilities and cannot explained by the model, right? That's a residual variability. All right, so, and that is nothing, right? Then, so the sum of squares of the model divided by the degrees of freedom for the sum of squares. So, and the degrees of freedom are the number of our predictors. Right? So, and the so the mean sum of squares for our residuals are nothing but the sum of squares for the residuals divided by the degrees of freedom of the residuals. And that is just, so the number of, so our sample size is the number of our observation units minus the number of predictors minus 1. So this additional minus 1, so we have to, we are losing 1 additional degree of freedom because we're also estimating the intercept, right? So that is an additional piece of information that we're losing, right? So one value less that is allowed to freely vary, right? So it's, so as we may remember, so degrees of freedom is always, so each parameter that we're estimating, so we're losing 1 degree of freedom. Okay, so And here we're estimating, right? So we have our, so for the linear regression, so we have one predictor. So our, that's our regression rate. So the slope for one predictor, so K would be 1. And then we are losing 1 degree of freedom for the intercept that we're also estimating, right? So, and if we basically do some very simple transformations, so we can see so how that this ratio here can also be expressed in the following way. Yeah, so we see how that is actually really a test of R squared. So, and it's nothing but so R squared again divided by the degrees of freedom. And so the so that's basically the explained variance, so the variability that is explained by our model, and this is the unexplained variability, right? So our residual variability is just 1 minus the explained, so the model variability. All right, so I included that only to show you that this is really a test of R squared. Alrighty, so and our f-test is called f-test because it follows the so-called F distribution. So the F distribution, other than our T distribution or normal distribution, is not symmetric. It's not bell-shaped, right? So it is asymmetric. So also our F distribution depends on degrees of freedom. And other than for the T distribution, so we do not only have basically 1 degree of freedom value, but we have 2. So we have 1 for the, right? So we have 1 for the model sum of, so basically the model sum of squares, and we have 1 for the residual sum of squares, right? So this is 1 degree of, so basically it is 1 value for the degrees of freedom, that is the other value of the degrees of freedom. So degrees of freedom for the residual variance, variability, and degrees of freedom for the model variability. All right, so, and the F distribution so has a different shape depending on these. So we call them the enumerator degrees of freedom and the denominator degrees of freedoms. Right? So the specific shape for the F distribution changes as a function of these degrees of freedom. So that is just one example here. So can look very different for other degrees of freedoms. And obviously our F statistics or our F value can be as small as 0. And that is the case when our numerator, so the term, so the R squared over K, which is just our mean sum of squares, so sum of squares model sum of squares, is 0. Yeah, if none of the variance in the outcome variable is explained by our model, so then F is 0. So obviously in this case, so we assume that R squared is 0 in the population as well. So and F approximates positive infinity if our denominator, so that means the residual variability, so the residual mean squares, approaches 0. Yeah, and in this case, if our residual variability approaches 0, so then it means all of the variance in the outcome variables explained by the model. Yeah. Well, in this case, so that means the larger F is, right? So the better, just in quotation marks, right? So the larger F is, so less likely it would be in the long run, always, right? Never forget that. Whenever we are talking about p-values and significance, always in your head add this phrase in the long run. That means over many experiments, right? So a single result never tells us anything about the population. It's just something that, right, like in the paper that you read, it's just something like as Fisher, so Roland Fisher originally suggested, it's just so if we have basically, so just one study that shows a significant, right, again, quote significant, like a result with a small p-value, then it indicates that there's something worth looking into, right? But that's why replications are so important. All the inference statistics is focused on the long run, right? So when we do that many times. So then always add that to yourself in your mind, right? It's not that if we find a small p-value, then something is a fact. or likely effect. It's just something that we might be worth looking into further. All right, so okay, so but if you like find a large f value, a really large f value, then so basically if that sample came from population where the true coefficient of determination is 0, so where basically our model is useless, where it's not possible to distinguish our model from the null model, so it's not better in predicting the outcome than a null model. So that would be very unlikely, right? So so the larger our f value, so the less likely it would be so to get such a result if the true R squared and the population were 0. So anything else that I wanted to say? All right, yeah. So and again, if you read something like that, so often you see like also f, and then as that the f has something in parentheses, like 2 numbers, and these are always the degrees of freedom for the enumerator, and then the second term is the so the denominator degrees of freedom. Yeah. And for our simple regression, I already told you that the degrees of freedom for our model are 1, and the degrees of freedom for our residuals are for our error terms are n-2, right? Because we're losing 2 degrees of freedom by estimating our 2 parameters. One more thing, and that is really important here. So the f-test on R squared is always one-tailed, right? It's always one-tailed. Yeah, so we're always looking at the right tail of the distribution, of the f distribution, because of course, I mean, what are we interested in? We are testing the hypothesis that R is greater than 0, right? So we're never testing R smaller than 0 or something like that, right? So we're always focusing on the right tail here. All right, so yeah. That is something that we will is particularly important when we talk about multiple regression. So I will repeat that. So blah, blah, blah. So I will actually, let me talk about that after spring break with the multiple R. So I don't want to confuse you right now. I will just talk about the adjusted R squared. All right. So unfortunately, our sample R squared is not an unbiased estimate of the true population R squared. Yeah, so it's biased. So, and it's biased upwards. So that means that it tends to overestimate the true population parameter. Yeah, so what we estimate from our sample, so our squared, so our explained variance in the sample is so it tends to be an overestimation. So our population parameter is normally smaller. So yeah, so that means when our true population parameter is 0, then on average our sample R squared will be greater than 0. And so the degree to which R squared overestimates the population, so the sample R squared overestimates the population R squared depends on 2 things. It depends on the number of predictors in our model, and it depends on the sample size. And the bias is the larger the number of predictors, and it's the smaller the larger our sample size, right? So it increases with an increasing number of predictors and a decreasing number of observations, so subjects in our sample. And so what we need to do is, in order to get a more accurate estimate of our population R squared, so the explained variance, right? So for our model, is so to adjust the sample R squared according to this formula here. And so we don't have to do it by hand, right? R is doing that for you or any other statistics program. All right, that's what I wanted to say about R squared. And so in the remaining minutes, let's talk us about this second, so an equivalent way of determining whether our regression model can actually be generalized to the population, so whether it's significantly better than a null model. And that is testing the significance of the regression coefficients, so especially for our slope parameter, right? So the intercept is irrelevant. And so the good news is that the regression B, so the regression coefficient B, is an unbiased estimate of the slope of the population regression line. So that's good. And so to test whether there's a relationship between our outcome variable and our predictor, right, in simple regression, so we're simply testing whether the slope is different from 0. And so, so that is, by the way, exactly the same as testing whether correlation coefficient is different from 0. It's absolutely the same test. So we have the same test statistic, the same distribution. And so that means that the sampling distribution of our B coefficients are similar to the sampling distribution of our correlation coefficients if the true parameter is 0 in the population, right? So also if our true B is 0 in the population, that means a sampling distribution that is based on random samples of the same size, drawn from the same population. Yeah, so this is a normal distribution. Yeah, where B's have a normal sampling distribution. And so due to the fact that we have to estimate the standard error for B, so the standard error of the sampling distribution. So the test statistic follows a t-distribution. Right? So the same logic. So we have to estimate the standard deviation. That's why the test statistic is follows a t-distribution. Right. And so again, so the test statistic is exactly the same as for the correlation coefficient, right? So for the case, the same degrees of freedom, for the case that's the true population correlation is 0. And just for sake of completeness, so the estimated standard error of our regression coefficient or slope, that means the standard deviation of the sampling distribution of B. So it's calculated according to this formula, and again, it's the same as for the correlation coefficient. And the reason why I'm showing this to you is that basically to demonstrate that it's a function of the accuracy of the regression equation, right? So this is just these are just basically it's just residual variability here, right? So it means it is the smaller the residual variability is. And it is the smaller the larger the variability of your predictors. So both make sense, right? And that's why it's also a reason why if we have restriction in range, right? So then typically our correlation coefficient is smaller. Right. So of course, so that is also the basis for estimating or calculating confidence intervals for our regression coefficients, right? According to the usual formula. So use the t-distribution, and then we just look up, so the quantile for alpha over 2, so where alpha is our desired significance level, and then, so of course the degrees of freedom, and that's just a standard error for B, right? And another thing, of course, that we can calculate in a regression analysis, also called a prediction interval, right? It's a confidence interval for our predicted values, right? Not for our coefficients, not for our regression coefficients themselves, but this is actually the confidence interval for our predicted values. So, yeah, so that means how much do they so basically it's just a confidence band, right? So that if it's like, so it's always hard to phrase that, but if it would be the 95% confidence interval, right, of our predicted values, then, right, so for each sample that we are drawing and estimating a regression model, and then we are basically calculating our y heads. So then in 95% of the cases in the long run, so this confidence band would includes the true y head, right? So same for confidence interval, right? Always think about it as the long run probabilities. All right. So, alrighty. So how much do I have here left? Should I get started with that right now? Probably not. Let's just stop here for today, and then we just save the multiple regression for so after spring break. Then we don't need to start a new topic today. All right. Okay.
Dr. Unger,
Yeah.
quick question. For
Yeah.
the midterm, is it up to the topics up to correlation? You're
Yeah.
not doing regression in the midterm, right?
No. So that's what I think
Okay.
I mentioned it in my email. So yeah, it's only correlation, so and no regression.
Okay. Thank you.
All right. So any other questions on today's topics or anything else? Oh, good. Yeah. Was it clear, so, or was it confusing? Because as I said, so it's really important to me that you understand regression. So, and if you basically tell me, then I mean, we have enough time. So overall, was it?
I think
I think-
it's doable.
Okay.
Like it was a lot to absorb, but I think it's
Yeah.
straightforward from the PowerPoints.
All right. Okay, good. So then don't forget, if there's things that were unclear or that are confusing, then let me know. Because can say it enough. So it's it's true. If you understand regression, so that will give you a foundation for understanding almost everything else. Alrighty, super. Then I will stop the recording.